And more or less immediately after that, he moved in to where he is now at TU Delft. And since 2008, he's been a full professor there. He's got a large number of awards I could run down, but one very special award, and I think above all, is the European Research Council advanced grant that he got in 2009. I wouldn't want to try and count all of his publications. I'm sure it goes over the 100 or so, and 200, I would say. Presently, he's department chair, TU Delft, and so Fulvio, we're tremendously pleased to have you with us today, and I can say for myself, I'm really very interested in your talk. So why don't you head off? Everything looks okay on my side here, so go ahead.
Thank you, Cam. Thank you for the very kind introduction. And I'm not chair of the department since a year, so I'm happily back to my full time professor and researcher role.
Okay.
I'm happy with that. So the topic I've chosen for today is data assimilation. And as Professor Tropea has already anticipated, this is a topic that is becoming very popular, and maybe we understand together why. But of course, I will relate data assimilation in particular to the context of a PIV as a measurement technique. Let's move one slide down. And what is data assimilation, or say, what's the aim? The aim is to put together measured observations and combine them with a model of a dynamical system. In fluid mechanics, then we have plenty of things that need to be modeled. The purpose is to produce more accurate estimates of the state of the system, or even of the future states of the system, so the evolution of such a system. And many data assimilation methods, they also produce uncertainty estimates. So what you see on the right here, I think my mouse should be visible, is that there is a satellite with a polar orbit that is mapping the atmosphere of our planet, and then takes atmospheric data. And this atmospheric data is combined with a model of our atmosphere in order to produce an analysis and forecast of the atmosphere. This was the case for the ozone layer. So in conclusion, data assimilation combines theory, mostly in form of numerical models, with observations. It will be important in the presentation today that I will speak about the goal as a goal to produce forecasts. So we measure at the time, but we want to make a forecast for future time or even previous times. And another role for data assimilation as used for PIV will be to have a interpolation, but physically informed. So using physical models to have better interpolation. And applications are more traditionally in the domain of weather forecast, but there have been application in experimental and computational fluid mechanics. So in the context of PIV, which type of data do we deal with? Planar PIV is typically dense, is obtained by cross-correlation, is on a Cartesian mesh. Tomographic PIV, pretty much the same, it's just not planar. It has some few planes or vectors also in the depth. Then we move to techniques that have been developed more recently, the tomographic PTV, again with the object reconstruction, but then with the sparse tracers and velocity field at the tracers. And then the state-of-the-art, very frequently used now, is a time-resolved particle reconstruction and tracking. Lagrangian particle tracking also mentioned, the shake-the-box algorithm that is very efficient to do that. It gives us velocity over full tracks at the sparse locations. And one of the problems that we encounter is, especially in aerodynamics, how do we obtain with PIV information with a temporal resolution that can compare with other instruments like the hot wire anemometer or laser Doppler velocimeter that are quite quick, but at a single point. So the problem for PIV sits in the requirements for hardware. I would say complex, sometimes expensive hardware, like high-speed lasers, high-speed CMOS cameras. And I mentioned here, Steve Baresh called his measurements at 40 kilohertz postage stamp time-resolved PIV, because the measurement can be only this small, because you have to concentrate all the light in a small region of space in order to have enough intensity. And for, let me see if this is, I'm moving. Yes, this might be better. Yeah, and for 3D PIV, you also have the so-called matchbox Tomo PIV. So the question is, if the velocity is higher, or in fact, if you haven't got that frequency, what happens? So if you measure at a frequency that is not sufficiently high with respect to the frequency of fluctuation of the flow, what will happen, what we encounter the most is aliasing. If we want to reconstruct a time series, we see, for instance, unphysical or unreal effects with the wheel of the car spinning backward, or even here with a jet where the vortices seem to go back into the nozzle rather than go outside. This is the phenomenon of aliasing. So how can we avoid this phenomenon still without having the frequency that complies with the Nyquist criterion? This will be the topic of today's talk, at least the first part of the talk. And we talk about pouring space in time. I like to imagine when you make a measurement, you have a certain spatial definition, spatial resolution. You also have a time resolution, and these might be like two glasses. And if I have abundant space information, I could imagine to pour part of that information into the time glass and see if I can improve the temporal resolution. So we're speaking of time supersampling techniques, and the objective is to increase the temporal resolution of the time series. How to do that? You can use models, and that's why we come into data assimilation. So a simple model is the model of advection, and that will be demonstrated on a wake of an airfoil. More complex and more general model will be the Navier-Stokes equation in a particular form, in the form of the vorticity equation. And I will explain that, how that model can be implemented on real data. It will be demonstrated for a transitional jet reconstruction in time. The second part of the lecture, if my chairman will be so kind, deals with the pouring time in space. So actually, when we have enough temporal information, but the spatial information is rather sparse. So this happens more and more nowadays when you do Lagrangian particle tracking or PTV, and you have this very highly defined trajectories of a few tracers, and then a lot of empty space around. And I will show that we can still use a framework of the vorticity equation and compare, for instance, what can be done with the vortex-in-cell technique compared to tomographic PIV, some classical technique. Finally, and this is a paper that should appear soon in Experiments in Fluids, I will propose also an approach where you assimilate not just a single time instant, but you can take a complete time segment, so a finite time segment. That's why it will be called the time segment assimilation. And I will demonstrate it, if time permits, on a turbulent cylinder wake. The time supersampling by advection is based on this simple equation. We measure at the location x and at time t. If we want to estimate also the velocity at the time t plus delta t, we could estimate it as the velocity at another location, slightly upstream of an amount that will depend on the convection velocity. So this is a technique that has been also used with many other instruments, but in PIV can be done very accurately because we have the velocity information in space distributed. So the hypothesis, this technique works in the hypothesis of frozen turbulence. So when the fluctuations are small with respect to convection, but also for time extension that is not too long, especially in presence of velocity gradient. And I will demonstrate it with presenting an experiment, and the paper is already now dated a few years ago. Is an experiment where we made measurements at the 20 kilohertz to have some sort of ground truth behind an airfoil, and then focused on this little point there. Then the procedure to evaluate how good is this advection reconstruction is to downsample the sequence. And here you see a velocity time history. The black line is the original velocity sampled at 20 kilohertz. And then you subsample it at less than 1 kilohertz, and you have these points that are connected by a linear interpolation. And finally, there is the supersampling by the advection criterion. So you can directly see that in most of cases, the linear interpolation, of course, is insufficient, but the supersampling by advection would work rather accurately here, apart from a few peaks that are missed. And if you look at the spectrum, if you want to make some spectral estimates, then you don't need to run an experiment at 20 kilohertz, but already 1 kilohertz would be enough, as long as you don't use just a linear interpolation, because that is very quickly truncated, the spectrum, and is also aliased. Even the part that is measured is affected by the part that is not measured. That's the aliasing. So I'm moving further. The question is, how can we supersample, how can we measure at low frequency also flows that are more complex, like shear flows? And I will give an example with this problem of this jet issued by a circular orifice. So the advection model, as we will see, breaks down if the turbulence is not frozen, and we need a more complete physical model. So we want to generalize the time supersampling, including also the nonlinear effect of advection, that is the shear and rotation. And to do that, I like to make a short example of which models, to what extent the model affects our prediction. If we have this tennis ball and we measure position and velocity at a certain time, we could decide to extrapolate, make a prediction for the future position just in a linear sense, and then the ball will continue indefinitely to travel upwards. We know, however, that it will not. If we would include just the gravitational force, we would have the rather correct, apart from aerodynamic effect, we would have the rather correct trajectory of this ball. And the model here is simple, and the ball is a single point. When we are speaking about distributed fluid and flow continuum mechanics, then you have much more degrees of freedom. And of course, you have the Navier-Stokes equation, and some terms are not even measured. So the pressure, for instance. So this is how then can we deal with the form of Navier-Stokes equations that can be used in order to produce such a forecast. And I will try to not spend too much time, but the idea is to use the curl of the momentum equation. That's the vorticity transport equation, time rate of change, the advection, and then the stretching term. And Christiansen proposed to discretize this vorticity field by vortex points or vortex particles, and then evolve the position of these vortices by advection and their strength by this stretching term. In reality, the algorithm starts from a measured velocity field. Vorticity is calculated by central differences, and then you discretize your vortex particles. Finally, you can advect and update their strength. Once you have done this, you have the vorticity at a new time step, and you have to interpolate it on a grid. To close the loop, we need again a velocity, and the velocity is obtained by solving the Poisson equation for the curl of vorticity. So this is all explained in the paper of Jan Schneider's from a few years ago. Let's see how this method would compare with advection, first on a turbulent wake, where we know that the advection should be valid, and with also high-speed measurements in this case, and on a transitional jet, where we know that the advection should have some challenges, in fact, for the core of these vortices. Okay, so for this wake, the way how I present the data is to take from the full data set at 2.7 kilohertz, I take a subsampled data set at only 675 hertz. And then I try to reproduce the missing samples. And what happens if I take a measurement at the frame 1 and at frame 5, and I combine them through this vorticity equation, I would obtain forward and backward time integration, the connection, the bridge between these two time instants. And if I take a point, I can make again a comparison with respect to the original data. This is the original reference sequence, and this is the one that is subsampled. And then the advection model, as you see, again, reproduces the wake, as no surprise with respect to the previous example. Also, the vortex model, in fact, does not differ much from the advection because it also contains advection. And the wake is close to a frozen turbulence. Let's move now to the, I will not do the error estimation because I predict I will run too short of time. Let's move now to the case of this nice transitional jet. Experiments have been done at 1 kilohertz. This is an experiment in water, so the velocity is only at best half a meter per second. The vortices are shed at approximately 30 hertz. So we expect that the sampling frequency should be at least 60 hertz. Instead, the sequence is subsampled to 25 hertz, which is less than half the Nyquist frequency. And there, we will try to reconstruct the original 1 kilohertz sequence by linear advection and with the simulation. And what we see is that this is the reference data. It contains some noise, but it's quite coherent in time. And then the linear interpolation in time produces a clear aliasing phenomenon. The vortices are not moving at all. And so this is really due to the insufficient sampling resolution. If we would use the advection model, the flow seems to move from the bottom to the top, but not much more than that, because the vortex dynamics is also completely distorted by the inadequacy of this of the advection for this flow. Finally, if we take the vortex-in-cell method, it looks like that the most important component of this dynamical system have been included because the similarity between with the reference is quite high. So this is just to say that if you take the original sequence, which is this, and you take points separated by even more than a wavelength, then it is possible by using the momentum equation in form of vorticity transport to produce an accurate estimate. I like to conclude. So some PIV experiments contain abundant spatial information, but that's truly usable only if you have a three-dimensional experiment. So I've shown how you can use this resolved spatial information to increase the temporal resolution. That's called the pouring space in time. The advection model is quite adequate, but for frozen turbulence, and the vortex-in-cell represents a more general extension of it. But so far, we have only shown that it works in 3D data, never in 2D data. And finally, I think this is quite interesting. We have to think about how we perform our experiments. In some cases, you don't have to run that quick with your acquisition, with your hardware requirements, because you can obtain back your spectral estimates even when you have sampled below Nyquist limit, if your flow falls into these dynamical models. So this is ends the first part of the presentation. And then I will go to the alter ego to this problem, which is pouring time into space. Why would we do that? Well, 3D often poorly resolved in space because you have to put all the spatial information on a 2D sensor. So often you cannot have that much information or the medium becomes opaque. And how to do that? We have to enforce governing laws that include the time history, this abundance of time information. So when you want to reconstruct 3D particles in space, I like to call it the Elsinga limit. There is always this problem that everyone asks, okay, but what is the PPP at which you are working, the particle per pixel? If you have too many particles per pixel, and this would be the case of these fog droplets, you will not even resolve anymore the space in between particles. So you will see a continuous smoke. If you make any reconstruction of that smoke, you will never retrieve the particles. So you have to accept to have less, dense seeding. And in particular, for large scale experiments, we are now moving slowly but surely towards HFSB tracers, so helium-filled soap bubbles that can produce a more sparse, homogeneous and also accurate tracing for larger volumes. But in that case, the distance between particles can be quite important, and we need to know what is the spatial resolution of these techniques. So there have been a number of studies on how to increase the reconstruction quality from sparse velocity fields. We can go back to Keen and Adrian. And super resolution approaches and solenoidal filtering that's been much studied, or optical flow, which is in that case a different approach. If you make some simple estimation, you find out that the resolvable wave number by cross correlation scales with the cubic root of the concentration of tracers. The same is for particle tracking, but the coefficient in front is significantly higher. So particle tracking has a higher potential for resolving smaller scales. And this is just a graphical example of the typical resolution and mesh that you can obtain if you make a linear interpolation or a cross correlation with overlap, and then if you would use a data assimilation technique. Let me move further. So I will explain again how VIC, the vortex-in-cell technique, can be used for to increase the resolution of sparse data. Another technique that is now currently used much with the shake the box is the flow fit from the DLR group. And then I will also present the concept of increasing the time, not to a single instant, but to a segment. So what we start with is a particle that travels along its own trajectory. We assume that it follows with fidelity the flow, and it's usually represented with a polynomial, with a Taylor expansion. And at this point, the problem is formulated as a minimization by a method that is a variational method. So you have a measured particle velocity and a velocity that has to come from a model, from a computation, say from CFD. And you put some constraints. This is the divergence constraint. The divergence of the final simulation should be 0 if you are considering an incompressible flow. So this is similar to data assimilation methods that have been proposed in the past decade. And the way how the VIC plus stands for vortex-in-cell, but the plus stands for the fact that you use not only the velocity, you minimize not only the difference of the measured velocity with the computed velocity, but also the acceleration, assuming that velocity and acceleration are, say, independent variables, is to minimize this cost function, J of u and J of du in dt. So this minimization is implemented in an iterative way, where you start with an initial solution for vorticity, and you march forward with the vortex-in-cell technique. You calculate the residual, and then you update it again. And this is done efficiently by a gradient estimation, by an adjoint technique. Let's show how this actually works. And the first assessment is numerical. It's a turbulent boundary layer computed by DNS, and where particles have been introduced artificially. And the approach was to consider different concentration from 150 particles per cubic boundary layer thickness, so per delta over delta cube, up to 4,000 particles. And a number of methods have been compared, from cross-correlation PIV, so like Tomo PIV, to interpolations, and finally including physical constraints. And what we see is that if this is now the DNS, the exact or the reference solution, the cross-correlation does quite poorly at low concentration, and it barely reconstructs a number of structures. When you move to interpolators, to some surprise, you can see that already a linear interpolation has a better resolution power of the cross-correlation operation. And adaptive Gaussian window is similar. If you impose that the divergence has to be 0, you obtain quite a high resolution. And if you also impose that the material derivative has to be matching the measurements, then you obtain something that looks denser. We have to see if it is any better. So these are the turbulent statistics, and this is the average velocity. Not much can be really inferred from it. And here you have low concentration, and here you go to high concentration. Of course, the data gets better at higher concentration. But then you see that with respect to the DNS, if you start considering U prime or V prime or W prime, the classical methods by cross-correlation or linear interpolation significantly underestimate the fluctuations, and already including the mass conservation makes a better job of this turbulence intensity estimations. Yeah, we applied it to a similar experiment. This was an experiment from Gerrit Elsinga and Yodai. So they realized the nice tomographic experiments. This is a video where they show the phenomenon of hairpin auto-generation mechanism. So they were quite happy because they could visualize, at least the time-resolved Tomo PIV was good to visualize this phenomena. But at some moment, and the bad news came when they realized that all velocity statistics have a reasonably good match with the DNS reference data. But if you look instead at the vorticity statistics, you get almost 50% underestimation compared to the DNS. And so there was quite a motivation to see how can we improve the resolution of this nice time-resolved experiment. And this was done with the VIC+ technique. And here is already a visual result. You can see this is the tomographic experiment, which shows the dynamics of low-speed streaks and hairpins. And but the rendering with the Tomo PTV and with the vortex-in-cell, this modeling really gives much more regularity. And finally, what was very interesting to see is that even the turbulent dissipations could be better estimated, except for a small region very close to the wall. But this means that the turbulent dissipation scales can be captured in a 3D PIV experiment. So now, if I hope that in 5 minutes, I can give you a glance of more of what I think could be also a future direction to look at. We have looked at a simulation of particles and particle velocity at one single time instant. And we know that the resolution will depend on the distance between these particles. The more particle we put, the smaller is the distance, the higher will be the resolution. What if we consider as a distance, not the distance between particles, but the distance between trajectories? So instead of this R in red, this R in black. You will see that if you take a longer and longer time instant, the distance between the sample trajectory converges to a minimum. And the question is, how can we use this temporal information without smoothing out, without making a simple time average, and produce a higher resolution estimate of the velocity field? And I have suggested it with this mesh that is a bit finer than the previous and the previous one. So this is the principle of time segment assimilation. The algorithm is a bit more complex in that it requires an initial condition of velocity, therefore vorticity, but then it optimizes not one single time instance, but all together a certain interval of time instance. So a computation over an interval that has to be compared with all the observations at this time instant. So the final optimization has to take into account these cost functions at every time instant. This is the algorithm. I will not enter into the details. I like to tease you that the article should be published really in a month or two, and you can see in the article all these details. But in essence, we propagate from a center point forward and backward, and we compare with the measured data and produce a cost function at each and every time instant, and then we bring it back to optimize the center value. This has been, I will jump on this point, but I will just present it by an experiment. An experiment was done on at a large scale. This is a wind tunnel that is 3 meter high, and a cylinder of a 10 centimeter diameter was put in a low speed stream. And this is already the result that comes from the shake the box algorithm. So these are the particle tracks. They look very dense, but if you make an analysis of their distance, the distance between particles is a centimeter or more. So the concentration is not very high. And at some moment, and this would be, for instance, the vorticity evolution in time past this cylinder. And then what I was interested in, and I think what's interesting, is to compare the reconstruction if you use only, say, almost an instantaneous information like this 3 frames or 15 frames or even longer trajectories. The first impression is that this result is less jittery. But you could also wonder, is it smoothed? And then also the vorticity is smoothed out. Is the resolution power the same or better or worse? And so looking at the vorticity isosurfaces, we can see that certainly the one with 3 frames has more noise, and then one with 15 frames. But we see that with a longer time history of the tracks, indeed, the structures seem to gather a few more details. So there is some indication that it has a higher spatial resolution. And I try here to convince you by showing what is the variance of the vorticity fluctuation as a function of the length of the trajectory. So we see that the 3 vorticity components tend to increase in amplitude when the trajectory is taken longer. And this means that at least the vorticity is not smoothed out, is not smeared out. And to show that this increase is not just noise, I plot here the temporal variation of vorticity, and we can see that it stays pretty constant. So the overall value increases, but its jittery fluctuations are not increasing. So this gives good confidence to show that this is a true increase of spatial resolution. Let me conclude here. Particle tracking gives us sparse velocity measurements. In large-scale PIV measurements, this is even exacerbated. Temporal information that is available by time-resolved measurement can be leveraged to increase spatial resolution. And I've shown you that using always the momentum equation in the form of vorticity transport, either in the Vic plus or with the time segment, one can produce this phenomenon of this process of data assimilation. I thank you all for the attention. And as a forecasting exercise, this is the weather in Delft.